So I guess it's 4, so we're going to start on time. So thank you very much for coming here. My paper is about can event study methodology keep up with cryptocurrencies. So this is co-authored with Denis Schweizer and Weiyu. So it's a little bit of an early stage study. We started it some time ago. It goes, as the title says, about event study methodology. I mean, event studies, nothing new. It's been around, especially in corporate finance, for quite some lengthy period of time. So it's been used to analyze stock prices, firm values, especially in the context of mergers and acquisitions, dividend announcement, stock splits, etc., regulatory changes. So any event you can technically think of. So now, why would I bring this up in the context of cryptocurrency? So cryptocurrencies, as we know, is not similar as stocks insofar that the return distribution are not normal, heavily tailed, skewed volatility also is not stable over time. So especially cryptocurrencies like Bitcoin have very different behavior than what we usually would expect with stocks. I mean, for stocks, we also find that they're not normally distributed, but not as bad as cryptocurrencies. So also what we see, sometimes we see those explosive growth. We've seen log2 returns, which are not data errors, but actual returns. So then the question arises, if we use traditional methods of event study to measure if an event is statistically significant or has a positive or negative statistically return, then do we actually measure bias? Do we measure something correct? Or what is it what we are actually measuring if basically we are violating all those parameters or those assumptions which are underlying? It has been applied, those methodologies, so that's the reason why I believe it's about time to have it looked at more closely. So we have, for instance, literature on monetary policy changes. So usually those papers find if there is a loosening in the policy, prices go up and vice versa. This methodology has been applied in the context of liquidity shifts, 51% attacks, regulation, war impacts, anything you can think of, airdrops, etc. So the thing is, as in corporate finance, the devil's in the detail. So typically what we do, we choose a nice event window, which can be 0, 0, -1, 1, etc. Typically, academics like some kind of symmetric windows for whatever reason. But we do not actually really have a good feeling about what the choice of the window has on the outcome of the study, for instance. Or what would happen if I would have chosen a different benchmark? So in corporate finance, it's more straightforward to find a fitting benchmark to calibrate your market model as compared to cryptocurrencies. In cryptocurrencies, it's not that you have so many cryptocurrency market indices readily available. So then it depends what kind of benchmark you're choosing. So this is mostly the motivation of the study. So we try to find out what influences the outcome of traditional tests we are applying. So we use the methodology from, or borrow some kind of the methodology from Marx and Musumeci, who also studied how well, especially two types of event study methodologies work in the context of stock returns. So this study was purely done on stock returns. So we are basically adapting their simulation approach and apply it to cryptocurrencies. So to gain more insight on what is happening. So ultimately, the goal of the study is to provide a sort of roadmap. What is the test and what is the benchmark we should use to not get or to get the least biased results? So that we do not have false positives or false negatives, which is very easily possible. All right, so data collection. So we work with 14,174 coins. So how do we get there? So we, it's shortened. So we take all the coins and token from CoinMarketCap. There's a P missing. So, and this is not limited to the cryptocurrencies which are currently listed in CoinMarketCap, but also includes by now DAT tokens. So everything which was ever listed on there, we kind of did a data crawl from July 1st, 2015 to January 2020 stream. So then we ran an extensive data cleaning mechanism. We had a nice paper before about the reliability of those kind of data vendors. I was happy to hear that CoinMarketCap at least scored an A. But then again, this is something I would like to work on as well to expand the database. So how strongly the tests are going to be biased depending on what kind of database or data provider you're going to use. Anyway, so again, it wouldn't make sense to include stablecoins, so we exclude those. We had in one of the presentations also some nice slides about the data errors, data mistakes. So we tried to kind of clean those data for mistakes or joke coins, pump and dump schemes, something like that. So technically what we require with this kind of method is that we don't want to have coins included which are just bumping up and down, because that's most likely data manipulation or too low liquidity or other reasons, but usually we would not consider this one maybe as a investment or kind of coin we would like to, which is seriously traded, let's put it like that. So the problem is that, especially when we're looking at the smaller coins, the CoinMarketCap is not that good to report market capitalization, and many papers I've seen usually have a minimum market capitalization to circumvent the problem with the data errors. So because this is a paper which is supposed to be more general, deliberately we wanted to have those cryptocurrencies included. So instead of market capitalization, we went on trading volume to exclude them. So if there's basically no trading volume, then we excluded them from the study. However, if there was regular trading volume, we included them even though we didn't have the market capitalization necessarily reported. But we also often see that cryptocurrencies which have log 2 returns, they are fully excluded. However, I try to look at some of the coins, and with cryptocurrencies, it's the case that some of those are actually valid observations. So we have seen this in the early days of Bitcoin. We have seen this with Dogecoin, Shiba Inu. So those are events that actually happen. So especially when we're looking at the credibility of a methodology, I thought it would be worthwhile to keep those included in the sample, because if this influences your benchmark, maybe that does have some implications on the results. And finally, I tried to remove that token, or at least the history. So I'm only including history when cryptocurrencies are actively traded. Once they stop being traded, then I remove them, because if you have only one trade, then the returns can jump easily. I have very big jumps, like not necessarily log 2, but high enough that it may disrupt the data. So if there is no regular trading anymore, I remove the remaining history. After all doing that, 14,174 cryptocurrencies are left in the sample to get you a little bit more idea how the sample is composed. Here is just an annual breakdown by year. So we are interested in 4 different categories of cryptocurrencies. The first is the top 100 by market capitalization. Ex definition, if market capitalization is not reported, then it would not be included on those cryptocurrencies. Then the top 100 by volume, so the ones which are traded most. So that could also include cryptocurrencies like Doge, which are en vogue at some point in time. And then more broadly speaking, large coins and small coins. So there are many papers which sometimes require minimum 25 million market capitalization. So that would be applicable for this group, and then put the remaining ones in the other group. So what you can see is in the 2015-2016, there were not that many cryptocurrencies which fit all the criteria. So I didn't find 100 cryptocurrencies with more than 25 million market capitalization ex definition, because the market was just too new. Looking at the year 2023, you can see that there is not that many large or very big coins as compared to a whole bunch of smaller cryptocurrencies. Sorry, I'm jumping between coin and cryptocurrency. I'm referring to cryptocurrencies. So this is the cryptocurrencies traded in that year, which are in that sample. So looking at some general descriptive statistics, what we see is that the median return for the larger and more liquid cryptocurrencies is around 0 daily returns. And if you're looking at the smaller cryptocurrencies, it's actually negative in the median, not in the mean. So this is already a strong indication there is non-normal distributed returns. And if you're looking at skewness and kurtosis, it's getting even worse, especially if you're looking at the smaller cryptocurrencies. So this is something which makes me ask, how would this influence the outcome of our standard test statistics, which are usually required: normal distributed return, constant volatility, etc. So how is the research design made up? So technically, after collecting all the data, we are collecting a random sample. So technically, what I'm doing, I'm randomly picking a coin at a random point in time. So it can be any coin in this history. So I don't determine the year. The only requirement I have that I have a sufficient number of observations in a 150-day trading window. So it's 365 days a year. So if, let's say, a coin would be discontinued after 100 days, it wouldn't enter in this random sampling. I allow for some data gaps. So as long as 90% of the data is filled, this cryptocurrency would enter as a potential candidate in the random sample. So, so for instance, I could have randomly selected the coin XRP, and then I use the first 100-day observation to calibrate my market model, which is done like in the standard event study methodology. So this is the estimation period. I stop 11 days before a hypothetical event date. As I said, I'm just randomly picking the coin and randomly picking the day. So that means there's got quite a high likelihood that there is actually no event on that day. I'm doing the random sampling to exactly have no event on that day, but I cannot rule it out. It could be that by chance maybe there is a day which actually has an event, but the point would be to hopefully through random sampling exclude that. Right. So then I can calculate the expected returns. So technically I use a kind of CAPM model. The market index I'm using is the value weighted index. I'm calculating based on the completed sample I have. So value weighted means the larger cryptocurrencies have a stronger weight than the smaller ones, and the more negligible that is. Right. So, and then I'm simulating an event. So meaning this way I can ensure that I know that there is an event or that there is no event, and I can calibrate what is the extent of the event. So I consider different kinds of events. First one, the non-event, so meaning I do not add any artificial return or volatility, I just leave it as it is. So technically I'm testing, is the test statistic measuring something even though it should not measure anything. So I don't want to have false positives. And then I'm playing around with the mean. So technically I'm simulating an event of, let's say, 1% daily return, 2% daily return, 3% daily return. If we are at 5, hopefully all methods should at least give me some significant result. In the first scenario, I do not consider it event-induced volatility. So I keep the volatility as is. I'm just adding some return which I already know beforehand. So I know what I should measure, and then I can backwards engineer to see what I actually measure. And in the second version, we know that typically if we are having events, especially if you're having regulation, or if it's not the coin-specific, cryptocurrency-specific events, then there could be event-induced volatility, which could disrupt our results. So in the second version, I keep my expected means, and I'm also simulating some event-induced volatility. The event-induced volatility is estimated from the volatility in the estimation period. So it's cryptocurrency specific. So it's not that I'm using like 10% for all the cryptocurrencies, but cryptocurrencies which have had a lower volatility in the past have lower event-induced volatility as compared to cryptocurrencies which would have had higher volatility in the past, which I believe would be more representative of what would actually have happened if there would have been an event. And then I'm calculating abnormal returns following standard methodology. And finally, I'm aggregating the abnormal returns to average abnormal returns over all my simulated events. So meaning that if I have the non-event, the average abnormal return should be 0. Meaning I do have my return, whatever that is, and I'm subtracting an expected return which is actually representative for that respective cryptocurrency, meaning that my model must have been good. So if my market model is good, then the expected return should be pretty much equal to the measured return. If my market model is bad, then the abnormal return is not going to be 0. And it's especially not going to be 0 in, maybe there are some idiosyncratic differences, but on average it should be 0 if my market model is good. And my beta is not kind of biased. So let's have a look what we actually get here. So I'm only presenting here the more extreme results, so the top 100 by market capitalization versus the smaller cryptocurrencies. And what we see is, here's my simulated event. So this is the case where I have no event. So I have a 0 extra return. It's just maybe random noise. And I consider one where I have absolutely nothing, or I have a scenario where the volatility of the market just becomes larger. But the expected return will still remains at 0. And then I have the two versions I previously mentioned. I have no additional event-induced volatility, but I know that I have now expected return added to my randomly drawn return. And in the second case, I have event-induced volatility. So as I said, if my market model would be good, my average abnormal returns should be 0, especially if the sample size is just large enough. If the sample size is small, like let's say 100, anything can happen because the sample is just small, too small. So this is what we see here. In the case of no event, I'm measuring some sort of abnormal returns, which can be either positive or negative. However, if we increase the sample size just large enough, it seems that my market model is doing quite a good job for the large coins. because my average abnormal returns are not significantly different from 0, and in the case of the 5,000, even 0. For the event return but no volatility, would expect here to see 1, 2, 3, 4, 5%. This is what we see. But the smaller the sample, the more deviation we have, because the market is just more volatile, you have more skewness, more kurtosis, more noise overall. So now the question would be, would any test, parametric or non-parametric test, still pick up that there is actually an event or not? So I guess I would be more positive if I'm looking at those numbers because they look like high enough, but this is not considering the volatility yet. However, if you consider that there is event-induced volatility, there is quite a lot of noise in the smaller samples. And typically what we see in cryptocurrency studies, the number of events usually are not exceeding really 100. So only looking at those numbers doesn't seem that reliable in the first place. So this is only speaking for the top 100 coins. Now have a look at the cryptocurrencies with less than 25 million market capitalization. You find some interesting results. So this is my non-event. And what you can see, none of those are 0. So this is already an indication that my market model is not really good for smaller cryptocurrencies. So meaning if I'm doing an event study and use, let's say, Bitcoin or a combination of the larger coins where it's easy to retrieve some data from as a benchmark, then I'm already pretty much off because my market model is already not good enough. So it systematically seems to incorrectly measure the expected returns. So my expected returns are systematically all below 0. That seems that I'm overestimating the beta. So I have a biased beta problem. That's the first one. Right. So let's see what else we have. So here, what we try to do is we try to put most of the most common event study tests there are. So starting from the most basic one, so the standard t-test, again, requirements, normal distributed returns, constant volatility, just to name the main assumptions. This already is not working that well for stocks, so I don't believe it should be working well for cryptocurrencies because we need to control that there is non-normality. There could be event-induced volatility, heteroscedasticity, etc. So moving basically from the top to the bottom, what is happening, all those tests adjust for one more criteria. So starting with the crude dependence adjustment, that means there is some deflation in the t statistics because we can assume that if one event happens, then there may be more stocks implied. So this is where it came from. As such, then we would technically overestimate the standard deviation and we control for that. In my specific case, I should not have that problem because I randomly draw my sample. So, however, as you've seen in my some of the previous slides, cryptocurrency or event study has been applied in policy changes. And if you have a policy change, this should be applicable for this type of event. So for that reason, I included this here as well. Then we have the standardized Patel Z-test, which supposedly adjusts to a certain degree that the returns are not normally distributed. Then we have a combination of those two tests, kind of. So we are controlling for cross-sectional correlation as well as non-normal distributed returns. And then we are, in addition, controlling for event-induced volatility. So as we move down the line, the test should theoretically address more issues we have in cryptocurrencies. So, and then we have those, need to speed up a little bit, the non-parametric tests. So here we don't test if the return is 10%, but we only want to know, is it positive or is it negative or is it just different from 0? So for the sign test, we just split it if it's positive and negative, and for the rank test, we also give some weight to the magnitude. And finally, the generalized sign test also adjusts for cross-sectional correlation. As I said, in my sample, that should not be the case. But for reason of completeness, I included it here. And finally, we have the Wilcox test, which tests if the median is different from 0, not the mean, which should kind of take care of the non-normality of the returns. So, so this is the first type of results. I only present a subset because there are so many different variations from that. So what we see here is I have an event which has 1% expected return and some event-induced volatility. If this would be a stock, all those tests would probably show significant returns. So now what's the case for cryptocurrencies? So I highlighted in green if any of those tests would basically not reject that it's not different from 0. So here I'm just testing, is it different from 0 or is it not different from 0? It's not, is it larger if it's smaller? So this would be an addition to this test. So this is just different from 0 or not. And what we see here, only in the larger samples do the tests pick up something. So meaning that the smaller samples, there's so much noise from the market in there that the tests do not pick up anything. Which is quite good in the case of my 500 observation sample, because by chance that had a negative return. Because it was just picking randomly noisy stocks or stocks which were on a downward trend, or the market model was not doing well. So there are different kind of reasons why that could be. So in this case, I wouldn't want that the tests would be significant. However, some of the rank tests are. So then I'm getting the wrong information. I'm getting the information, yes, it's different from 0, but I may falsely assume it's negative even though it's positive. The higher the expected return we are simulating, the more stable become the results. So basically in cryptocurrency, we need quite a high jump in expected return. So there needs to be a pretty significant event so that the standard test going to pick up the right sign. On average, what we find is the rank and sign tests are more sensitive, but the problem with the sign tests is that they sometimes have false positives, or even give you the wrong result because they're picking up negative returns even though they should pick up positive returns. On average, we would have expected that so from the left to the right, the test becomes more sophisticated, it corrects for more issues. And this is what we find here too. So the more simple tests don't show significant results, even though they should show significant results, which is probably due to the non-normal return distribution. The further we get to the right, the tests control for a certain degree of non-normal returns, and as such, they also show a significant results. If we move to a return of 3%, all the tests show positive. So technically, it's also a little bit of an issue, not that the test may be not good enough, but if your expected return is not high enough, even if you're using a better test, you're not going to find a significant result. Final table for today. So this shows what is happening not for the top 100, but for the smaller cryptocurrencies. And long story short, technically for the smaller cryptocurrencies, we already established that we have a bias in our market model. So we can expect that the tests itself are already biased. And then the cryptocurrencies on average are also more noisy. They suffer more from changes in volatility, more jumps. And as such, if we have this 1% return and event-induced volatility, all the parametric tests only by chance pick something up. But it's not a reliable result you're going to get. So you really, for smaller cryptocurrencies, it's important that you have probably at least 3% daily return that you measure something. And now imagine if you're extending the event window, let's say 3% is the total effect of the event, and if this 3% are spread over 3 days, you have so much more noise that technically with the standard test, you're not going to find anything. So you need much more. So final one is, so what test should we now take? So what I've now presented was a little bit of on the negative side. So which one is now the most reliable one? So good story is, so this is technically redoing the same sample all over again. So let's say here is my sample size 100. And I redid this experiment 80 times. So I'm drawing a random sample of 100, then I'm drawing another random sample of 100, and another one, another one, another one, just to see if what is the outcome, because 100 is quite small, right? So it could be that my first results are just random because I picked the wrong 100 observations. So I wanted to circumvent that, and I used all my 8,000 observations I've drawn and split it in blocks of 100, and then checked on average which test gives me the right result, because I know the result, on which one gives me the wrong result. And I tried to color highlight which ones are good in green and which ones are bad in red. So good news is that for the parametric test, there is a very low chance, or there is actually non-false positives, so at least we don't get wrong results here. However, there are sometimes tiny mistakes. So they are right in 96% of the cases to 94%. So if we now try to pick up an actual event, if the returns are just so small, we're talking about 1 and 2%, it's a 50-50 chance that you're going to get any result, or even less. So only if your return is high enough, there is a sufficient reason to believe that you're actually measuring some statistically positive returns, if they are there. So otherwise, it would not be the case. If you have event-induced volatility, the picture looks even worse. So meaning you need, if you would use the standard t-test, or the crude adjusted test, it's too unlikely that those tests show some significant result. So you would need to use some more sophisticated tests to ensure or increase your probability that if there's an event and this event has some significant, in this case positive, you only use positive returns, then we would need to use at least some kind of adjusted Patel test, which adjusts for the non-normality, or the standardized cross-sectional test to increase your chances. Again, this works quite well, or better, if you're talking about the larger cryptocurrencies, so only for the top 100. However, if you're moving down to the smaller cryptocurrencies, it gets quite messy. And the main issue is, in my opinion, that the market model is not working well. And if the market model is not working well, then there is too much bias in my estimate. And I mean, if you're looking at this, I'm simulating a 5% daily return, which is quite high. with some volatility, and some of my tests only show me a significant positive return in 83% of the cases, which is, in my opinion, too low. Right, so again, there's a lot of work to do. So what I would like to do is those rank tests on average are picking up much more. However, they're also likely to pick up the wrong sign. I haven't included that information yet, and due to the time, probably there's much more to do, which can be done. What I would like to do is test how, for instance, an equally weighted index would work for smaller cryptocurrency, or if a factor model would work better. Some more distinction between the rank tests, etc. So this concludes my presentation for the day. Any questions?
I have a question. Can you go back to your simulated table where you build in returns for the 5, 1, 2, 5? Yeah, for the top 100.
Yeah.
Okay. So as an example,
this one.
In this 2,500 column, you're really very close to 5, 4, 3, 2, 1. And or actually all of those. Did you test the significance of whether that 5%, that average, is that an average? Is that what that means?
This is the average abnormal return.
Yeah. So did you test the significance of whether that 5% was different from 5? Because that's what we would expect, right?
I did some tests, but I didn't report it.
Okay, so is it different?
So this is not different from, so all those are not different from 5%, 4%, 3%, okay. But the further we move to the left, we cannot reject, so we can, I do not have, I should have put stars.
No, that's just fine. I just was wondering, because I think I understood what you were doing, but I didn't see whether that was, if you tested them against 0 or what they were supposed to be, and you did, okay.
Yeah, so that was mostly a sanity check if the simulation is good enough and if the market model is doing a decent job.
So in the top 100, it's always the same top 100, or over the sample, do you have lots of movement of?
So technically, what I did.
No, I'm talking about the top crypto market cap.
This?
Yes.
No, it's just random. So I picked a random coin and checked if it's in the category, in which category it falls. Then I picked another coin, checked if it fits in the category. And for top 100 is market capitalization, so it must have fulfilled the requirement that in 50% of the event time it was falling in this category, because I have 150 days and theoretically at the beginning of the event period could be below. It's not in the top 100 in the end, it's in the top 100, so it needs to be in the top 100 in the respective quarter, kind of.
But your top 100 is on market cap, right?
Yeah, and it's moving. So basically every quarter I'm checking what are the 100 on a kind of quarterly basis. I'm not sure if I put 3 months or 4 months.
Yeah, no, that's fine. Okay, so it's changing. The top 100 sample is changing. Yeah,
I mean, you have some Bitcoin, Ethereum, they're usually in there all the time, right. But other cryptocurrencies, they keep on going in and out.
Okay, fine. Okay. Good.
Yeah. Same for market capitalization, smaller and larger than 25,000, and also for the volume.
Yeah.
So it's the only thing which I'm kind of recycling is technically I'll only choose 8,000. And I put this random 8,000, which is an independently drawn sample, but I do with, I'm not taking one event twice.
Okay.
So there is not Bitcoin on August the 25th twice in there by chance. I removed those. So it's 8,000 different cryptocurrencies and dates. But I have no distribution. Honestly, I didn't, because I randomized it, I just give them a random ID. So I could not tell you in the end which have been drawn. So I could not tell, okay, I mean, most likely Bitcoin is there in more often because the time series is longer.
Right.
But I can't, I couldn't give you in detail what, if there is a bias in there.
Well, I mean, my expectation would be that top 100 is going to be relatively more homogeneous in structure than the bottom 25. I mean, less than 25 million, because those are going to be dying and living, coming in on a quarterly basis.
However, I found it still interesting for cryptocurrency event study because it's not always the larger cryptocurrencies which may be subject to interesting events like, let's say, airdrops or something along that line.
Okay. Yeah,
So if you have marketing stuff, then maybe it's more the smaller cryptocurrencies which are more prone to offer those kind of events.
features.
Features. Features.
Wonderful.
Other questions? Then thank you very much for your attention.